Hello and welcome to the latest Office Hours webinar by Bit Gardner. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. If you're unfamiliar with our Office Hours format, it's typically a shortened presentation, usually 20-25 minutes, followed by open discussion and really answering any questions you may have, any challenges you have at your facilities, or anything we can help in terms of today's topic, or even beyond today's topic around color, appearance, and physical testing. Today's topic, however, controlling color, gloss, and grain. We have our application specialist, Mr. Noah Morgan, presenting and answering questions, moderating. Also, if you do have a question during the presentation or even during the discussion, please log that in the chat box located in the bottom right-hand corner of your screen, and we'll get to that. If for some reason we do run out of time, we'll follow up with you individually to make sure your questions are answered. We are also recording this, so immediately following the presentation, you'll receive an automated marketing email with a link. Please share that with colleagues, listen to it later, grab some screenshots, whatever you like. And always too, if you have any questions that pop up down the road, you can hit reply to any of these marketing messages. It'll come to my team and we'll route it to the appropriate technical person in your area, or one of our application specialists like Noah. So here we go. Noah, how you doing? Are you ready to roll?
I am ready to roll. Thank you for that nice introduction.
All right.
So like you said, today we'll be talking about controlling color, gloss, and grain with the spectro2profiler. All right, so to get into it, to start, uniform appearance is an important quality for many different products, especially when it comes to multi-component products. The problem is that our visual quality perception is influenced by things like color, gloss, and your surface structure. Visual rating takes all three of these parameters into consideration, and then we can make an overall judgment, whether that material would pass or fail if this was in a manufacturing setting. Up to now, spectrophotometers and gloss meters were available on the market with improved technical performance for matte surfaces, but things like surface grain had to be controlled either visually or with highly sophisticated microscopes. This has now changed with the introduction of the spectro2profiler, which takes into account your color, your gloss, and it measures your surface structure. So we'll get into a little bit of how that works. So with this new approach for objective measurement, we have a combination of many different measurement techniques, all put into one instrument. So to start, we'll go over its color measurement capabilities. So we have a typical 45-0 geometry setup. What that means is if you look at the side view here, we have illumination coming from 45 degrees to the observer, which is a spectrometer, which is directly overhead of the surface that's being measured. So it's measurements or lights coming in from 45 degrees and measurements being taken at 0 degrees. If you look at the top view there, we see that there's 6 different LED lights that are putting this illumination out over the surface. They're all 60 degrees from each other. The good thing about this setup is that there's 6 different lights, meaning that we have a circumferential illumination. That's nice because no matter what the orientation of the instrument is on a surface, you'll always get the same color measurement results. So diving into the gloss measurement here. So this instrument includes a 60-degree traditional gloss measurement according to the international standards. A side view of what that looks like internally is we have the illumination coming in from 60 degrees, and then we have a detector at the opposite angle, again at that 60 degrees to pick up that specular reflectance. The issue with this type of setup is as you increase your surface texture and you get a lot higher structures, this type of gloss measurement can cast a shadow and create what we call shadow zones, and these shadow zones can then falsify your gloss result because you're no longer getting that light that's been lost in those shadow zones as a reflectance. So to combat this, we came up with the 2D reflectivity measurement. And so what that is you can see it here. We have an inline illumination. So we see our light comes in from the side and hits a beam splitter, which then sends the light directly down to the surface. And then all of that light then gets reflected back up towards a camera. And what this does is it helps to eliminate those cast shadows, so we have no shadow zones. So we purely get the reflectance value for the surface there. So here we can see the two side by side. So we have the traditional 60-degree gloss measurement, and we have our 2D reflectivity measurement on the right side there. And just it's a nice comparison between the two. But essentially, all it does is, our 60-degree gloss measurement can sometimes get these shadow zones when we have high structure. And that can give you false information. It doesn't tell you the full story of what's happening. Whereas this inline setup helps to eliminate those cast shadows and then provides a full 2D reflectivity data set across your entire surface that's measured. So what we see here, we see a nice image. This is a reflectivity map of a powdered coated surface. So in this map here, we see that the black pixels represent low reflecting areas, whereas the white areas represent reflecting areas. The brighter it gets in this map, the more reflectivity is on the surface. The value for each pixel can range anywhere from 0 to 500,000. So it's quite a big range. And the camera is referenced on a black trap with a value of 0 and a matte white reflectance tile with a R value of 2,500. So the measurement area that this instrument can take is 15 millimeters by 15 millimeters with a resolution of 512 pixels by 512 pixels. So that means if we can take all the reflectivity values for each pixel and then average them, and then what we end up with is a mean reflectivity value. And in this case here, for this specific sample that was measured, we have a mean reflectivity value of around 11,572. So what's nice about the mean reflectivity value is it can then show you, valuable information of how that surface is reflecting across the entire surface, not just a few sections of it. So in addition to the gloss and 2D reflectivity values and measurement principles, we have an additional 3D topography measurement. And how this is done is we use another technology called photometric stereo technique to get the 3D topography. Essentially what is done is you have four different light sources at different angles, and the camera overhead takes pictures as these different lights illuminate the surface. And from there, you can estimate the surface curvature. And then once you estimate the surface curvature, you can create a height map based off of the object. The result is a real 3D topography of the measured object surface. And then you can compare those topographies to further analyze the differences between grain structures or grain types, for R&D purposes or for quality control purposes. Here's an example of how the internals are working behind the scenes. So from a side view, we again have our camera directly overhead, and we have our illumination coming in from 60 degrees to that camera, angled down towards the surface of the object. From the top view, we can see that those illumination LEDs are 90 degrees from each other, and there's 4 of them. And from that, we have our height map on the right side here, and you can see that it's a powder-coated surface, and it's color-coded, which means that the colors in the purple area represent the valleys of around negative 50 microns, whereas the orange color represents peaks, at around 30 microns. And then around 0 microns, we have the average height of all the points. So that's a nice 3D topography graph that you can see. And it's very nice for comparing the different surface types that you have. So again, this is our spectro2profiler, which includes our 45-0 color measurement with our 60-degree specular gloss measurement, our 2D reflectivity, and also our 3D topography. So it has all these different capabilities within the same instrument. So it's nice as a one and done tool that can help in any type of process that you have. So with that, we kind of spoke over the internal geometries and the measurement principles behind it. But now what we'll do is we'll dive into the actual mathematical calculations and algorithms and what the actual values you'll get on your material and how those are useful. So to start, the instrument itself has three or four different types of algorithms that it can use for different types of surfaces that you'll measure. So from one being powder coatings, we have what's called a coarse paint algorithm. It's meant for random structures that aren't patterned like leather-like. And then we'll move on to the leather-like, which is in the middle here. We have a leather-like algorithm, which is mainly for car interior. What we're looking at there is basically your grain size, your grain height, how far the grain is from each other, so that grain spacing. And then we have what's called our fine algorithm for very fine textured paints or parts. Usually you'll see it on plastic parts, on computers, and some small electronics. So to dive into the leather-like algorithm, unfortunately we'll just be on the leather-like algorithm today due to time's sake. But to get started, we have 3 samples here. So sample 1 with grain type A, sample 2 with grain type B, and sample 3 with grain type C. So what do we see as differences between these different samples? To start, we can see a clear difference in the grain size and then the grain height. So for an example, sample 1 has larger cells, if you can see it closer. Sample 1 has larger cells and more spacing in between the cells, where sample 3 looks like it has a lot more cells. They're a lot more smaller. So it's just a nice differentiation between them. So can we measure what we see? Yes, we can. That's the determination of the mean cell size, which is our CS value or a grain size value, and then the mean cell amplitude, which is our height, our CA value. All right, so here's a height map of the 3D topography measurement from the top view this time. So what we see, it's color-coded again. So the purple areas represent the valleys, and the orange areas represent the hills or the plateaus. So if you think about measuring an area like one of these surfaces we just saw, this is a small cutout of that measured area. So just a 5 millimeter by 5 millimeter section of that total measurement. And it's nice because we can see how we segment and how we determine what is a cell. So we do that by the segmentation, which is called the watershed segmentation. And we do it by the drop of water principle. And so what that basically means is if you have a topographical map and you go to drop little bits of water into that map, it slowly starts to fill up, almost like how a mountain. If you have a mountain and the valleys get filled up with rivers, it's the same concept. And what you're able to do with this is as you slowly fill up those valleys, you'll eventually have just little islands floating around it. Those will be your hills and your high points. And we can then take that size of that closed off island, and that becomes a cell in itself. And so we can then take each of those cells and calculate our cell size, our total cell area across the entire measurement, and then our total cell size with that. Here's another image to show you what that means. So again, if you had raindrops coming down over these hills and they slowly filled up the valleys, then cut off each of these high points from each other, and then you could then classify each of these different points, each of these different tall hill parts as their own cells. So topography segmentation is done by the drop of water principle, like rain falling onto the surface. The water accumulates as rivers in the valleys between the hills, and the rivers define closed cells. All right, so moving on. So here, this is an example of a picture taken out of our software. So on the left side, you see the raw 3D topography data in grayscale so that you can see the lines better. On the right side, you can see the watershed segmentation. So the green line equal the rivers, and this is where all the topography is divided into cells. So since we know the dimensions of the optics and sensors, we can then calculate the area of each cell. So that means if we average over all single cells captured by one measurement spot, we can get the mean cell size, which is our CS value. And this is the average of all these cell sizes across the entire measurement area. So we can then take this value and then compare it up against different samples. And to do that, again, we see our initial samples, our sample 1, 2, and 3, and they're now classified based off of cell sizes. And so we see sample 1, it sits around 2.61 as a cell size. Sample 2 is around 2.95, and sample 3 is about 1.59. So what that shows us is that sample 2 seemed to have the largest cells, whereas sample 3 had the smallest amount of cells. So if we go back to that original image here, sample 3 has the smallest cells across the entire surface. That seems to be true. And then sample 2 has the largest cells out of the 3 samples here. So that also seems to be true. And again, it's not by much. We're looking very, at very small values in this. All right. So moving on, this is still within the leather-like algorithm, but we have the determination of the cell amplitude. So this is an example here of a master plaque that has 5 different samples on here. And the difference between the sections are the grain depth. So our actual grain depth here. So our big portion is the 100% grain depth, and we see, it's very clear the differences between the hills and the valleys. And as we go down to 80, 60, and 40, down to 20, we see that it slowly starts to get flatter and more shallower. At 20%, it almost looks like there's no, it almost looks like a smooth surface. That's how shallow it is. So how can we measure what we see? We can do that based off of our mean cell amplitude, which is our CA value. And how do we determine this? So here we have an example of how this is done. So on the left side, you see the 3D topography data with the segmentation into cells. Within every cell, there's some maximum and minimum points, which are the red and the blue crosses here, or the red and blue circles. By calculating the vertical distance between those 2 values, we can get the cell amplitude. And then if we average over all the cell amplitudes in that measurement area, we can get the mean cell amplitude, so our average cell height. With this, we can then go back to that initial master plaque there and correlate our visual perception to what our measured values are. And so we see with our 100% grain depth, we have a CA value of around 150. And as we go through all of them, we eventually get to 20%, which seems to have the most shallow appearance. And we see that at that point, our CA value is around 60. And something to note here is that our measurements here are done in perceived height rather than actual height. This is because you can have some cases where, a difference in color. So if I had a black leather-like surface versus a white leather-like surface, our actual grain depths could be exactly the same, but the white sample will appear a lot shallower than the black sample based off of just based off of the color. Because it's a lighter color, it's not going to give that much contrast in it, and it's going to look a lot shallower versus the black sample, even though they have the exact same grain depth in reality. And so it's important to know that when we measure here, we're measuring in perceived height. So here's another example of a different value that we can use. So samples with different gloss appearances. Across the 4 samples that we see, we can see differences between 1 and 2 and 2 and 3. So 1 looks like it has a lot more contrast between those hills and valleys, whereas 2 looks like it doesn't have much contrast. It looks a little shallower because of that. So how can we measure what we're seeing there? We can measure that via our reflectivity contrast value, so our RC value. And how do we determine this value? So here we see, let me pull it up here. So here we can combine the 2D reflectivity with the 3D topography data sets. Since we measure with the same optics in the same spot, every pixel can then be paired with a certain height value. And then you can combine this with the respective reflectivity value, and then that can give you your RC value based off of the calculation on the right. So if we know the reflectivity of the hills and the reflectivity of the valleys, we can then use this calculation to calculate the contrast between them by subtracting them and then dividing through the sum. So that's how you can see this reflectivity value. And so now when we look back at those initial samples, we see that the value measures a clear difference between them. And so sample 1, we see as a very high reflectivity contrast value, whereas sample 2 is the lowest there, lowest out of the 4. And then sample 3 and 4 are pretty similar to one another. So it does show that we see a visual correlation to this value, and that can be very useful in determining how well samples pair to one another or how well they appear when placed next to each other. All right, so that just sums up the leather-like algorithm. Again, there's 2 more types, and there's also a 4th type, what we call the reverse leather-like algorithm. And that is essentially for a more modern type of textures where everything's inverted. So instead of being protruding from the surface, it's going into the surface. Usually you see more hexagon shapes or more geometry type shapes for those materials. But this was just an overview of the leather-like algorithm, and for time's sake. So if you have any questions, please feel free to put that in the chat, and we'll get to those at the end. And then we'll just overview our spectro2profiler again. So we have, again, that 45-0 color measurement. We have the 60-degree specular gloss measurement. We have the 2D reflectivity measurement. And we also have that 3D topography. So with all of those different measurement principles inside of one instrument, we're able to accurately depict exactly what we're seeing and what we're looking at, so that it can be the same every time for a quality control aspect, or exactly what you're looking at for an R&D aspect. All right, so that's it. If you have any questions, please let me know, and I'll give it back to John.
Hey, thanks, Noah. Good stuff as always. Got a couple questions coming in, and like Noah said, if you have anything else, just toss it in the chat, and we'll get right to it. Hello, we're a paper manufacturer and emboss paper products with various linen, stipple, and finer patterns, typically on low gloss, less than 5 gloss 60 surface. Which surface structure settings would you recommend? Is there a way to compare paper surface test results directly or as a ratio to the perfect negative pattern for the embossing the rolled surface represents? That's a lot.
Yes, yeah, it's a great question. So it really depends. I'd have to see the surface to really figure out which settings would be best for it. But off the bat, you mentioned stipling. Let me pull up this here. So it could be perfectly fine with the coarse paint algorithm. That seems to fit most things. But you could also dive into the leather-like algorithm a little bit as well. Really, it's hard to say without seeing the sample or at least viewing the sample. But you should be okay with the coarse paint algorithm. And then once you have, those measurements of your different paper, you can put it through our software, and then you can compare the 3D topography maps directly right up against each other and really see how they differ from one another. You can look at the scale on the side and see where they differ in like micron size or perceived height size. But I think this tool is pretty good at differentiating these different types of surface structures on materials. So
Good. He wrote a follow up here too. They have multiple spectro2 profilers and have some measurements on the instrument using a linen cloth pattern.
Yeah, it's very interesting. I'd like to, outside of this, if we maybe talk on the side,
Yeah.
Look at your different material one-on-one. That could be pretty useful.
Yeah. Mark, take a look, copy down Noah's email address and feel free to ping him directly. Because one of the great things about Noah's group, they can take samples, do tests, in our facility, and carry on that ongoing discussion to find the best solutions for you. So definitely reach out there. Let's see, another question. Do you see any issue measuring surfaces other than leather with smaller imperfections?
Yes, so I don't see any issue with it. It really depends on what you're looking for. I have some applications where people have used this instrument to look for imperfections on surfaces.
Yeah.
Because with that 3D topography data, you can really see, a zoomed in version of what you're looking at, from a distance. It's a great question.
Yeah.
I'd love to hear about the application, so feel free to shoot me an email. We can talk more about it.
Yeah. Good. I mean, aside from, leather, we talked about paper, painted structures, plastics. What are the other types of materials that, you've found that this instrument works well with?
Yeah, so really, I mean, it's so many things, right?
Yeah.
Anywhere from, the surface of a painted wall to the plastic parts on your computer.
Yeah, that's true.
Really anything. You could really just pick up an orange and measure an orange and get the measurement on that orange as well. It really, anything that has any type of surface quality or surface texture that we can see, this instrument's able to scan that very well, using those different types of principles in it. And then you can see, all those different values that can sometimes correlate to exactly what you're looking at, depending on what it is you're measuring.
Mm-hmm.
But for the most part, it's pretty accurate, and it can really show you a lot of what you're looking at.
Nice. Are there, I guess, substrates that surprised you in your testing and working with a multitude of industries and markets? Something that just really is like, wow, this really works.
Yeah, sure thing. So, a lot of energy drinks and different cans that companies
Ah,
are making have different textures now. Um, and so it was interesting to see, the texture that they're putting, these stippled textures on some of these cans. Um,
that's interesting.
we're able to measure it accurately with this instrument, and it can really depict differences between how that paint's sticking to the surface, or the spacing between those cans, or the spacing between those textures. It's very interesting. That was one of the ones that surprised me.
Yeah, I mean, you normally think, oh, automotive interiors, that's the easy one, but you get into papers, like our participant mentioned, cans. That's some cool stuff. Very cool.
Oh, for
Um,
sure.
are there limitations to the gloss?
So no, I think you're referring to the wave scan. I know there are some limitations to that instrument, but for this one, there are no limitations for the gloss level. So,
Nice.
with the LEDs and luminance that it uses, you can get, you know, you can measure really any type of surface and get data from it.
Nice. Nice. Okay. Yeah, keep the questions coming in, folks. This is your time here to play Stump the Noah. How about that? Um, Question here: does the software that comes with the device, does it provide advanced filtering, separating, and analysis of the texture data specifically? I know it does the color and gloss, but
Yeah, yeah, absolutely. I want to see actually if
yeah, do you have
I'm
any examples
able.
you can pull up?
Yeah, give me 1 second here. Okay. I'm going to share my screen real quick. Okay, so this is our software here. So this is just some quick examples, but I'm going to select some different samples here. And then I'm going to compare. And so this is what I was talking about earlier with the 3D topography comparisons.
Yeah.
But for example, if I select one of these measurements here, I can zoom into this. Hide this here. I can zoom into the surface really as close as I need to, and from a you know if I were to look at the surface normally without measuring, I couldn't see this much detail. But because I'm able to measure it, I can really look into the detail of the surface, and then with these different values that I went through earlier, you can really compare what's different between these different samples. So if I select maybe this one here, look at our 3D topography.
Yeah.
So these are, again, this is our watershed. So like I spoke of before, how it differentiates between different cells with the drop of water principle. As you fill the rivers up, or in this case, as you close off those cells, determines what is a cell. And see, these are from our different measurements there. To sample one. Comparison. I have to select another sample here. Okay, so if we select this one, so right now I selected two different samples, and if I zoom in, visually I can tell a very clear difference here. But when we look at the values numerically, we can also see that they're very different as far as cell number. So how many cells are in each of these samples, our cell size, our average cell amplitude, our reflectance is fairly similar. Our not fairly similar, but we have a reflectivity contrast our reflectivity for the hills, reflectivity for the valleys, our hill sizes, so how big are each of these, the average hill in these samples, our fill factor, so this is our space between these hills, our cell size minimum, so our smallest cell size, our cell size maximum, so our largest cell size. This sample here is most likely this is our largest cell size there. And then we have our standard LAB data and then our gloss value here. So really with all of this, the software is very useful in finding differences between our samples. So
Yeah.
hope that helped answer your question a little bit.
Yeah, it's good to see the software. Thanks for pulling that up for us. Another follow-up here regarding the paper. When using the fine texture method, I saw 11 readings displayed. Is that like the number of measurements? Or Mark, would you like me to unmute you? I've just unlocked your microphone. If you'd like to elaborate, you can now unmute yourself. If you'd like, it's in the upper right-hand corner, a red circle with a microphone in it. If you just click that, your microphone will be on, and you can elaborate on what you're seeing and how we can assist. Give him a minute here. Yeah, or you can type as well. We can see that. You may not have a microphone connected. Calibration. Can you talk a little bit about that, Noah? How often does it need to be done? What standards are required? Things like that.
So we recommended the same as most of our other color instruments.
Mark, let me interrupt you there. Mark, you there?
I believe I am. Sure.
You are. Welcome. All right. Ignore my last question, Noah. Mark, it's all yours. How can we help?
So we have been using this device to measure kind of a wear on some of our embossing rolls, some of which are rubber in nature and some of which are chrome and steel in nature. And I didn't have access to the software, so I was really excited to see that visualization of things. But and anyhow, and fooling around and not having too much information, I just went to the fine structure because I had a very fine pattern that we have been using. I think the leather-like pattern on one set of and giving a single. I think we've only used just a single number. I think it's the CA cell amplitude, the design. But then going to the finer structure or the setting, all of a sudden 11 different readings come out, and I believe cell amplitude is still one of those. But I don't have it right in front of me what all the numbers were or what they stood for, but I think you would probably recognize it. I think so. Anyway, we're using actually a linen cloth-like would be one example of a paper texture. Linen, a linen cloth pattern is really what it is, and so that we have a roller that has the negative pattern of that to press into the paper, of course, and so we have different variations and loadings and widths of paper that we do, all of which affect the texture, the ultimate texture. So trying to quantify that and then set up control parameters is kind of what we're hoping to do. So when you go to a much finer pattern than linen, for example, then and I think a car interior might be to that next step possibly, but it is an ordered pattern, But they typically, when they do an embossing pattern, they might nest in 4 by 4 inch squares of a pattern to make a continuous pattern on a roller, so you don't see any seams and things like that. But anyhow, it still is an ordered kind of a pattern, if that helps in determining what settings to use. But certainly we could share samples in the future and just to get to a better understanding of what it was. And so I'm looking for the more somewhere where there's a resolution difference where the numbers change enough that they were not changing enough. Once you go to a finer structure pattern, the cell amplitude wasn't giving me enough resolution. So that's
Right.
what I'm trying to make that jump from. Maybe cell amplitude is good in one case, but I think it probably is even richer if it has the finer structure or finer patterns, if you will.
Right. So something important to note is, with the finer algorithm, it's really meant for, those really small micro textures. And so with that, when it records the values, it's, we normally record it and, just the whole value, but in the fine algorithm, it uses micro. You'll see the micro symbol in front of all the values. So it's making sure that everything's super small. And so when you look at your amplitude, you're no longer looking at the full cell amplitude, but now you're looking at the micro cell amplitude. So it changes that. I'd really be interested in just, seeing, maybe we can share the samples and talk offline and really find the best way to measure those types of specific samples for you.
And I've got a couple different colors, but mostly the shades we use are the gloss levels are quite low, less than 5 on the gloss 60 scale. But interesting piece of equipment, though.
Yeah,
for sure.
Definitely. Well, let's we'll follow up with you, Mark. Noah will get you Mark's contact information, and you can send some samples. We can do some testing just to optimize things for you and make sure you're getting what you need.
Sounds good. Thank you.
You bet. Appreciate it. All right, Noah, back to calibration.
Yes. All right. So calibration. So almost the same as with our other color instruments. Typically, every 2 months, we recommend to calibrate it. It comes with the color and gloss test standards and a white calibration standard. So with that, it's the same as our other color instruments. You have your typical white calibration standard, and then you have your checking standards, which are your color and your gloss.
Nice. Okay. Let's see. What can you go over again the measurement geometries and the illumination and viewing angles?
Yep.
Specifically around the texture.
Okay. So this is the illumination angles for the color measurement. You have your 45-0 geometry with your 6 illumination angles. So you have your 6 different LEDs, which give you that circumferential illumination. So light's coming from all directions rather than one direction, which would affect if you were to take a measurement in a different orientation as your last measurement, you would get different results because light's just coming from one direction. And when you have it coming from all directions, that means no matter how you orientate it, you're always going to get the same value. As far as for texture, we have our topography measurements, so where you use photometric stereo technique, which is essentially just illuminating an object with different light sources at different angles, and taking a picture of each one of those. And then you can look at all the shading between the different pictures and calculate how that surface structure is, that you can put or calculate the topography of that object from those images. And then we also have, again, the 2D reflectivity. So that uses the inline illumination. So you have illumination directly overhead rather than just from the traditional 60-degree angle as a normal gloss meter. Because the regular 60-degree angle gives you these shadow zones, so it falsifies your results. It's not truly an absolute measurement. And that's why we add not only 60-degree gloss, but we also add in the 2D reflectivity measurement to give you a full representation of how that surface is reflecting.
Nice. Thanks for going into that for us. Keep questions coming in. We got a little bit of time left here. One more thing, at least for me anyway, in terms of the RA limits, measuring, very high or very low roughness textures. Have you run into any limits, in pushing the instrument and the technology?
Yeah, I personally have not run into any limits. I also, not going to say I've tested the most crazy types of materials. But so far, everything I have tested with this instrument, it's been able to really pick up exactly what I'm looking at and then some. Because you can, specifically that 3D topography data is very nice to look at. It's something visual to look at. Normally with these types of instruments, you're always looking at just numbers. So when you have something visual to look at too, where you can then zoom in and really see that surface. I think for me, it makes a big difference. You can really see what's going on. Not only can you, compare the numerical values, but then you can also compare how those 2 3D topography maps look compared to one another. So I think it's a very nice tool that the software provides as well.
Yeah, and that software comes with the device, right?
Yeah, so the instrument comes with 2 software licenses, so you can put the software in 2 computers, and it's free. So you can just download it from our website, and once you have the license installed for it, you're good to go.
And let me throw that link in the chat here. It's under support and then software on the webpage, bic-instruments.com. So you take a look there and can download the Smart Chart. I'm scrolling through looking. Oh, Smart Lab and Smart Process for the profiler, right?
Yep. And so what that specific version will do is that'll download a 30-day demo trial. So if you don't have your licenses on the software yet, you can download that, and it'll give you a 30-day trial along with the entire software package.
Perfect. And too, if you run into trouble, just hit reply to any of the marketing messages you get, and we can hook you up with Noah or one of the other applications folks. Let's see what else. Okay, I think that's all the questions we have in here. If there's anything else, get it in now. Going, gone. I know everybody's busy, so I don't want to ramble on any longer than I need to. All right, so we'll, like I said, you'll get this recording, including the discussion, via an automated email. So take a look there. Thanks for attending. Thanks for joining us, Noah. As always, big thanks to you. I learned something new every day. We could do these things, so I appreciate it. And hey, have a great day, rest of your day, everyone out there. And we'll look forward to seeing you on future webinars. So have a great one. Thanks, Noah.
Take care.